Today we're going to continue to talk about the reverse engineering. Announcement. Last time I mentioned about this hackathon. I just forgot to mention that in order to attend this hackathon, you need to register first. So please make sure that you register so that you can, join this hackathon. And in case that you don't know about this hackathon, so this is a hackathon that is gonna teach you how to fuzz. If you don't know too much about fuzz, you can just consider fuzzing as an automatic tool that can help you find vulnerabilities from projects, like your written program or like large open source projects. And actually, the goal of this hackathon is to first of all teach you what is fuzzing, how to fuzz, and second, you're going to be tasked to write some easy fuzzing, harnesses, which is like small program that can connect further to open source projects, so that you can fuzz open source project and find vulnerabilities, and you'll be rewarded, with actual like dollar. If you first of all, if you learn it, you'll have some cash, and then 100. And then if you manage to really write some good harness for an open source project, you will get more money. But beyond just money, it's a good learning experience. And if you are interested in doing cybersecurity as your career, I highly recommend you to join this hackathon, because it's going to teach you a very popular used technique in the world. All right. Oh, and also, students are emailing me about this hackathon, asking me like, if they need to know anything about fuzzing, any kind of background prerequisite for this. My answer is no. You don't really need to know what fuzzing is. It will teach you what fuzzing is, so you don't have to worry too much about if you have enough background to know it. Given the fact that you are in this class, given the fact that we are going through those essentials about software security, cybersecurity, you're good to go. So don't worry. And then if you're interested, I highly recommend you to register it. All right. So I saw a question saying that it's $100 for 4 hours. So it's not really 4 hours. It's just this like a learning process. And the learning process is going to probably take like 2 hours. I think that they just have a conservative estimate for the number of hours that you can spend over there. But they're not going to pay you by hours. Basically, they're going to pay you by the process, which is like you learn fuzzing, or you manage to make some good progress writing these harnesses. If you can write harness in half an hour, you'll get the money in half an hour. It's not really just a matter of time. All right. Cool. Okay. So today, let's continue to talk about interesting thing about reverse engineering. I will first start with x64 assembly. Please let me know. Have you read assembly before, or do you have any classes that teach you assembly? I want to know just like if everyone knows about x64 already, or you need to know more knowledge. Okay, I saw some of you guys raise your hand. That's great. So already know x64 pretty well. It's okay that you don't know too much about it. I will say, x64, it's like language. So it's like you learn a language, like you learn, say, French, given the fact that you know English. There share some similarities. And the even nicer part is like, as long as you kind of know the grammar, like the structure of those instructions, it's going to be very easy for you to catch up. All you need to know is just Google it around, look at those operations, look at those meanings of those semantics, and then you'll catch up very quickly, like you have a dictionary with you. And today I'm going to just go through this, as a basic, just a very essential, very basic introduction about x64, in case that you don't know about it. And given those knowledge, all you need to do, the rest is, if you don't know about it, the rest is just look at those dictionary, like Google, have those x64 instruction set, and then check this reference whenever you come across any instructions that you don't understand. All right. Cool. Okay. So first instruction, let's start with this. Push RBP. So can someone tell me what push RBP means? All right. No one knows what push RBP means? No? That's okay. We're gonna learn it right now. So let's start with this instruction. And you see that this instruction is composed of two parts. One is push, and the second part is RBP. All right. And the first part, it's like the verb, like tell you what operations that you're gonna do. And that part is called remind. So it's like it's gonna tell you the action that you're gonna do for this instruction. And then the rest of it is called operand, like RBP. Sometimes you will see the other instructions that may have multiple operands, but here in this specific one, it has only one. Okay, so each instruction is composed of one mnemonic and multiple operands. And push RBP, it means that you want to push the value of this, you know, the value of this register, which is RBP, it's the register, to the stack. And anyone know about stack before? You guys know about stack? Good. Okay, great. So it's like stack is, first of all, you know that stack is a data structure, right? So it's a data structure that you know, last name, first out. And in the computer, like in the operating system, we have a stack maintaining all the time by the kernel. You know, so that every time that there is instruction saying like push RBP, it will, you know, just push this value into the system level stack. All right. And then RBP is a register. You know, it's an operand in the, it's called an operand in the instruction, but also RBP itself is a register. So let me know if you know register before. No? Okay. Yes. Awesome. Good. Yeah. So you can consider register as a CPU level, you know, variable. It's already there. Like they already declare the variable, and you can use this variable while you are executing the instructions or running a program. So it is a specific location, like it's a like physical, you know, specific location that a CPU is be able to visit very quickly. So it's like different from memory. It's going to be much faster, you know, if you just use register. And that's why, in fact, if you are doing like compilation, if you have a compilation class, and the compilation class talks about optimization, one of the compiler optimization is to maximize the use of register and minimize the use of memory so that your program, while executing, will get a better performance. So different architecture will have different notations of register. For x86-64, you know, for this specific instruction set, we will have those registers. Those are, to be more specific, this is for x86-64. So you see that, you know, we have RX, RBX, etc. Those are 64-bit register. And there are also lower, like, you know, registers with little, like with fewer number of bits, although that is resided under this like 64-bit register. Basically for a CPU, it has those 64-bit register, but also you don't have to use the entire 64-bit of this specific register. You can only use part of this register, which is also noted as, you know, like EAX or EDX, you know, those represent lower 32 bits of registers. And similarly, you can only use like 6-bit, 16-bit, or 8-bit, and there's also representations that denoting those, the lower part or half or a quarter part of this register. And then back to you know, push RBP, we are using like RBP as the register. But again, we're not really, because register itself is like a, you know, a specific location at CPU. All we do is not really move that to the stack. We just copy the value from RBP and then push that value onto stack. And then in stack, in operating systems, in Linux systems specifically, the stack always just grow from the higher address to the lower address. So here, I show, suppose this is the stack, and those stacks are items by items, and this is the lower address, and this is the higher address. Okay. So once push happens, it copy the value from the operand, which is RBP in this case, and then make that value show it in the lowest address, like in the current lowest address of the stack, which is the bottom of the stack. And there is a specific register that will always show the current lowest address on the stack, which is stored in the register called RSP. So the RSP is a register that is responsible for storing the current lowest stack address. And by the time that we do push command, like push instructions, such as push RBP, RSP will be automatically deducted by 8. Because in this case, we're looking at 64, 64-bit operating system. So that's why every time there's a push happens, it's going to be deducted by 8 bytes. So it's like RSP is going to be deducted by 8. Okay. So far, so good about push command. You're going to come across push for many times in your assignment, software security part. So make sure that they do understand push RBP. It's very important. All right. So next, let's take a look. Move instruction. Move RBP, RSP. Can someone tell me or maybe guess what this instruction is talking about? Yes. So again, it moved the value from which register to which register? Okay, cool. Yes. So this instruction, it moves the value from RSP to RBP. So you might find this a little bit counterintuitive because usually, we read sentences from left to the right? But then here, it actually moved from the right-hand side to the left-hand side. It's a little bit different from like this copy command that we use in Linux. And we will talk about why this is counterintuitive later on. Okay, and then again, move is the mnemonic. So it tells you the verb, it tells you the operations that you're gonna do. And here, RBP and RSP are operands. Those are like the objectives that you're gonna work on. Okay. So as I said, this move RBP RSP, it looks counterintuitive because it moves from the right-hand side to the left-hand side. And sometimes, for just a ease of reading, for a ease of understanding, some of you may prefer, looking at those instructions and then move from the left-hand side to the right-hand side. So this is just a matter of representation. We call it syntax. There is a so-called Intel syntax, which shows, this operand in opposite order. And there is another AT&T syntax, which shows it in a more natural way. So you might prefer AT&T syntax because it just be more natural. But by the time that you read assembly, I want you to make sure that you can tell which syntax that you're reading. Because if you just read a random assembly, looking at these two commands, these two instructions, you may be confused. And because of those confusions, you may mistake the source and destination. So for Intel syntax, basically, each register will be represented as just 3 letters, just pure letters. However, for AT&T syntax, those registers are going to be started with a % sign. So you can use that as a way for you to distinguish between these two syntax and use that to tell which syntax that you're reading, if you're reading a disassembly or assembly. Okay. And later on, I will tell you, the pro accounts for ANTAX and AT&T syntax. And right now you may say that AT&T is better because it's more natural, but it's not always the case, which I will show you later on. Okay, so operands, we just see a register, and there can be more different kinds of operands. It can be an immediate value, just like a constant value, like 0, 1, 2, 3, whatever. It also can be a so-called absolute memory address, meaning that you want to access the value that are stored in that particular memory, and then the address of the memory is stored in RCX. So for example, if RCX has a value, saying it is hex 8000, then this move instruction, when we have this specific bracket, it means that you are gonna access the memory with the address of hex 8000. And then here keyword means that once you access that memory, you need to figure out how many bytes they're going to read starting from that memory. And keyword tells you that you're going to read 8 bytes and then move that to the register of RDX. Okay, I saw questions asking me to use it. I am using it. Let me just increase the volume and let me know if this doesn't work. Hello? Hello? Better? Okay. Let's continue. So we talk about absolute memory address. And you see that from the third instruction, there is also another representation. Great. Let me have issues with display. 1 second. Let me just open it. Here we go. All right, let's continue. I'm sorry for the pause. Okay, so the next, another different representation about memory is that you can specify a base address of this memory as well as an index. So this is similar. This is going to be similar to the way that you access an array. So for example, if you already have an array, you already have an array with a couple numbers of elements. Then you're going to access one of those elements, say the 5th element. Okay. So in order to access that, X6 has this nice representation which support the way that you can index to find this 5th element. Index is 5th element directly using the scaled indexed memory representation. So in this case, RAX represents the index. Basically, if you're accessing the 5th element, then it's possible that RX is equal to 5. And then 4 here is the number of bytes for each element. So once you see represented like this, you will be able to understand that what it's trying to do is to access the argument or access the variable starting with RBP minus 48. And then starting from there, treat that as an array and access this RAX array, basically.
Oh,
So this is about move instruction. Again, move instruction, there are, it can has a different different types of operands. You can move an intermediate level to intermediate, you can move an intermediate number to a register. Also move the value from memory to register. And then to represent.
मुझे नहीं पता, मुझे कुछ भी चलेगा.
Either just use absolute
सारे कपड़े तो आप ही डिसाइड
to
करें.
store
मुझे नहीं पता, मैं थॉट्स में फाइन नहीं लिखता, मैं फाइन
preference that, or you can use
नहीं
the
जिंग नहीं
scale
पहन
index
लेता हूँ.
preference to access a specific memory
अरे
and
काली
move
बस
value to a register. And also you can move from
नीली हो रही है,
register to
ये
memory.
पॉकेट वाली है, इसमें बहुत
However,
पॉकेट्स
for
है.
x64
और क्या,
you cannot move
वो
value
क्रीम
from
रहने दो.
memory to memory.
हाँ,
Other
ये छोटू है एक तो.
we support that. So
ये
just keep in mind that
नहीं,
for
और ये भी,
64
ये
you
भी.
cannot do that, but it doesn't mean that any instruction, any architecture that cannot do it.
ओके.
All right.
वेल मैंने तो भी पुराने दो निकाले थे.
All right, so now we have more instructions. If you're going to have an instruction like this, first, figure out what syntax it is. So again, this is Intel syntax, because those registers, they're not starting with a percent sign. All right, and then the next step, we're going to read this. So this is a comparison and jump. So this is a conditional jump instruction set. Usually the way that it works is that you're going to compare two values and then figure out if these two values, one is larger than the other one or smaller than, or etc., depending on the condition that is specified in the conditional jump instruction. And then based on that condition, you're going to decide to either jump to the the address that's specified in the condition jump if condition is satisfied, or you just continue, like execute the next instruction right next to the jump instruction. Okay. So in this specific one, JGE means greater or equal to. So in this case, in these two instructions mean that if the RAX value is larger than RBX current value, then you jump to this specific address. Otherwise, you continue, the next instruction right after, followed by JG. And pay attention that right now it is Intel syntax. And in fact, if you look at AT&T syntax, it will be a little bit different. The order of the two operands of the compare instruction will be different. So instead of having the left-hand side is greater or equal to the right-hand side, you need to flip the order. So here it is RAX, pay attention, this is the right-hand side of the compare, instruction. So it is the right-hand side that is greater or equal to, like satisfy this condition, to the left-hand side RBS, and then I jump to this. The cons part, the cons of AKT syntax is that whenever you read a condition or comparison instruction, you have to flip the order of those operands. Okay, and then another different type of instruction. We talk about push. Push has one operand, and then move has two operands, and you will also come across like sub, add. They're also like two operand instructions. And then we have the comparison. We just talked about that. And then now this is another different kind of instruction. It is the third instruction shown over here. The instruction has a prefix, and for this three instructions, it means that you want to repeat until ECX is equal to 0. Basically, you set ECX as a value, and that is hard-coded. So it's like, you cannot specify other register to become this like kind of a loop iterator register. So ECX has been hard-coded to become this loop register. And then once you have an instruction like this, starting with wrap, it means that you just repeatedly execute this, this instruction into ECX is equal to 0. And one time, like once it executes, ECX will be selected by 1. All right. So that's a very brief introduction about x64. I just show you different types of instructions, instructions with different structure. But that's pretty much, all the structures that you will come across for x64. I mean, you know the structure, but you don't know too much about the vocabulary yet, given that, when I don't talk about it too much. So if you're not familiar with x64 before, then you may start to confused by those instructions if you don't know those, like the meaning of those mnemonics or the meaning of those registers. But again, just as I said, it's like you learn a foreign language, but you don't have to really like learn this language by understanding all the instructions, because you're not going to learn all the vocabulary for each language. You're going to have your dictionary. You know the grammar, you know the dictionary, and then if you come across any sentences that you don't know, you just look in the dictionary and then find the meaning of those words. And similarly here, there is instruction reference. If you just search x64, instruction reference online, there'll be a bunch of those online resources. And then you can just use that as a dictionary while you are reading assembly. And just like you learn other languages, people will say, you're encouraged to read more, so that you will make this more natural in your mind. Similarly, you also want to improve your ability by reading more assemblies. All right, so resources, since I just mentioned about dictionary. So this is an instruction reference online. You can use that, or you can check the cheat sheet. It's a 1-page, I think, if I remember correctly. It has like takeaways, quick takeaways for the meaning of those instructions. All right. Okay, so now we're gonna have a quick practice. The assembly is right-hand side, and I give you 3 initial values for 3 values for the registers. There are initial values for those 3 registers. And my question here is, what's the value of ECX and EAX in this after executing these instructions? I will give you a couple minutes to read and try to, kind of like dry run it in your mind, and then let me know the value of ECX and EAX. And you can also type me on Zoom. I will track Zoom's chat. Did you see anything? All right, I saw someone coming up to me. Suppose you're done. Good, you got it. Awesome. Let's just hold for a second and wait for the other people. All right. Let's work on this together. I am going to copy paste this instruction to a notepad and we can, so that we can write and annotate over there. 1 second. All right. You should be able to see my screen right now. And let's work on this together. Remember that we say the value. So EDI is 10. ESI is 20. And EDX is 40. Okay, so we're gonna go through those instructions one by one. And then track the value of, especially for EAX and ECX, because that is the question. Okay, before I talk about first instruction, first of all, let's take a look at this. What's the syntax of those instructions? What's the syntax of them? Intel? Yes, it's Intel. Okay, so now we know that once we have any, like a move or add instructions, the destination register, the destination operand is the first one. And then the source is the second one, just the right-hand one. Okay. All right, so first EDI is equal to 10. And then we have the first move instruction. So it moves from EDI to EAX, right? So EAX in this case, then it's going to be, which is equal to EDI, so that's 10. And EDI is still 10, right? Okay, and the next instruction, ECX, move ECX, ESI. So ECX will be equal to ESI, which is 20. Okay. All right, next comparison. Because this is Intel, we know that the JGE asks if EAX is greater or equal to EDX, right? And then we know that the EAX value is 10 and the EDX value is 40. So in this case, EAX is smaller than EDX. That means that we're not going to jump to greater, right? So we just continue to execute it. We come to the next instruction. Now we have the add instruction. Again, the destination is EAX. So add means that EX is going to be equal to EAX plus ECX. And we know that the EAX value is 10, right? ECX is 20. So the sum of it is 30. Okay. And now let's continue. The next is it's going to sub ECX from EDX. So it's going to be ECX is equal to ECX minus EDX. Okay. So what's the value of ECX? It's 20. What about EDX? That is 40. Right? So now we have minus 20. But pay attention here. You know, those registers, they do not have a kind of like so-called negative. So once we come across a negative value, we need to convert that to unsigned value to the 64-bit register. And I will talk about the conversion later on. Let's just finish this instruction, finish this here. All right, and then it jumps to end and it just return, and then program is done. Okay, so EX value is 30. This is the final value, right? And then now let's talk about how to convert the ECX negative value. So it is negative 20. And in order to convert a negative value to an unsigned number, what you need to do is to have this negative value and then to end the 64 bits, like 64 bit, and every bit is denoted as 1. So it's like this FFFF, 8 Fs. How many Fs actually? I think it's FF is 1 byte, and then we're 8 bytes. Okay, so it's 16 Fs. I don't know if I write enough Fs. 1, 2, 3, 4. Because, you know, again, this is 1 byte, another byte. And then for 64-bit operating system, 64-bit architecture, we have 8 bytes. 1, 2, 3, 4, 5, 6, 2 more, right? Okay. So that is the number that we need to end with the value of 20. And you can just easily pop up in Python file and then do that. And make it looks a little bit better. Let's just convert it to hex. And this is the value that we have. This is the final value for ECX. So ECX should be equal to this. Okay. All right. Let me know if you have any questions. Okay, one question from Zoom. What if EX is greater or equal to EDX? So if this if the condition is satisfied, so if EX is greater or equal to EDX, it will jump to 9BF, which is labeled as greater. So it will jump to this address. And then followed by this address, it will start to do an add instruction, and then jump. Okay. All right. Let's come back to the slide. So as I said, EX is equal to 30 and ECX needs to represent -20. And for unsigned register, you need to convert -20 to unsigned value in 64-bit. So you just XOR that and you'll be able to get the final answer. All right. Okay, so those are all about assembly. Next, let's start to talk about reverse engineering tools. So ultimately, the so-called reverse engineering, or say like those reverse engineering challenge that you will probably come across, is usually just like, okay, give you a binary and you read it, understand what it's trying to do, and then, you know, try to extract the flag. It's like solving a puzzle. If you answer the puzzle correctly, it will give you the flag. And then I would say there are many kind of, you know, different reverse engineering tools. It's because now it's so advanced, you know, for this technique, it's like you're going to shopping mall and then select whatever kind of a product that you like. And different people will have different preference. You may hear, you know, debate about the Ghidra or item. Someone prefers Ghidra, someone prefers item, or some more, you know, other debate, or okay, what is the best, say, GDB plugin that you like? You know, what is the best debugger that you would like to use? So people will have debate, just different taste. I am introducing to use some tools, but this doesn't mean that you are bounded, you're restricted to only using those tools, and you have the freedom to choose whatever your tools that you prefer, as long as you can, you know, finish your task. Okay, so some static tools. So static means that you're gonna just treat a binary as like a file, as an article. You just read it without really executing it. And this is the so-called static tools. Basically, it just eyeball it, but of course with tools, it will automatically parse the information statically. So for example, if we're given a Linux binary, you can use readelf, you know, to get the elf information, because it's elf format. This is why it's called readelf, and we already used that in our last time's lecture. Or opstomp. So opstomp, it applies to not only just elf binary, it also applies to, you know, like Mac binary, or I think, yeah, and also I think PE, like Windows as well. So opstomp is a good tool that you can use to get those information, like the binary's instructions information. Or you can just read the bytes, although, I mean, few people read the bytes directly, but you also see that last time what I try to do is I can open the file and then read the byte. So Hackathon is a good a command, or say like a snippet that can help you with that. Or if you just, you know, want to read the disassembly, you can use opstomp. And the technique that opstomp uses for, you know, disassembly is called linear sweeping. I'm not going to give you more details about how disassembly works, but if you're interested in those kinds of techniques, like how to convert from machine code back to assembly language, assembly instructions, this itself is actually an open science. It's not 100% solved yet, which means that, you know, although you probably want to be able to come across that, but like in some complicated programs, you will
come across some situations that the disassembly that you see, from tools such as Opsum is not exactly the right disassembly. Some of those code, like the data, might be mistaken as instructions. So you may see some weird instructions. And if you do see so from Opsum, don't panic. It doesn't mean that this instruction still exists. It just means that it falsely consider a data as instruction and then it disassembled it. All right, so that's about static tools. And of course, we can execute a program. So then we could use dynamic tools to execute it and understand what this program is talking about. You could use GDB, the debugger, when you execute it. But GDB is not very user friendly. No, it doesn't have any colors, and those commands are, just like you reading a command line. Usually there are a lot of things just popping up right away, like all those things together, and you have to read it lines by lines, and you have to type many commands again. It's pretty low level. The nice thing is that we have better, higher level plugins that you can install with GDB together, and they will give you better visualizations and also like a higher level, more abstract information, which is nice. So you could use Pada or Jeff or PoundBack. This three, I think it's probably three of those most popular plugins. You can choose whichever you like. I have people that our students love Jeff. We also have students that love PoundBack. I personally like PoundBack better, but it doesn't mean that you can't love Pada or Jeff. Just, again, this is a shopping mall. You're gonna just play around and choose the one that you like the most. Oh, and there is even a post about the pro and cons people's. It's like writing a review for a restaurant. They write a review for those different plugins, and you can take a look and make a decision based on those pro and cons listed over there. All right, and then we like static tools. We can read it, it's very quick. We also like dynamic tools because you can execute it. But sometimes you want to have both, or even more, you want to have more advanced features. And for that, you can take a look at these 5 different tools. Again, this is not an exhaustive list. There are more. You can just Google it. I think IDA and Ghidra are probably some more popular or more used tools. You could check that online. And Ghidra is free. And IDA Pro, it has a free version. You can also just use that. And the nice thing for Ghidra is that it has a decompiler. It's a pretty workable decompiler. Decompile means that you kind of reverse back from a binary to a source code, basically. So using Ghidra, you'll be able to kind of have a recover the source code, although sometimes it doesn't really look like the source code that you write. It's good enough for you to get a good understanding for the program. Okay, as I mentioned, those are different reverse engineering tools. Opsum is a disassembler, which is part of the reverse engineering process, and those are also techniques. There are techniques that are used in those tools. For example, disassembler. Disassembly, disassembling techniques, it has different kinds of techniques. Linear sweep means that you just start with a particular byte and then read the following bytes and then convert that to instruction. And after you finish disassemble one instruction, you just go to the next byte right away and then still consider that as instruction. So just like you recover those instruction by instruction, bytes by byte. But sometimes it can be wrong because there might be data that are mixed into the code. And then that will be some alignment, just like, no op there, but you will still consider that as an instruction, although it's just a that code. or some, alignment, which is just maybe like 0, 0, but it's not really instruction. But if you consider that instruction, disassemble it, because you just do that byte by byte, instruction follow instruction, then you may mistake it as instructions. And there's another way, it's called recursive traversal. The way that works is that you again start with instructions, but then whenever you disassemble it and found a jump, you just jump to, wherever, like the destination of the specific instruction. So in that case, it's like almost guaranteed that you can find the right instruction. You're not gonna mistake data as instructions, but the bad part is that you may miss some of those codes that have never been jumped before, or that have never been, jumped to whatever instruction, the entire functions, entire programs. For example, if you implement a function, but you never call this function, then recursive traversal will not be able to touch that function, because you will never come across a jump statement that, or a call statement that will go to the specific function. Okay, and there are paper, as I said, this is open science. There are papers that are talking about those automatic reverse engineering techniques. But in general, so far, automatic reverse engineering is still an open science problem. It's not 100% resolved. But if you are interested in this, like would like to advance those techniques, make it better, you are welcome to talk to me and join the Subcom lab, and then we can work on some interesting stuff together. All right. So now we have another in-class attempt. We have an example. We have a challenge for you to reverse right now. There is a key in this challenge, and you can download the binary from this link. Like the first part is the course website, and then slide example.out. You can download the binary. And I want you guys to work on this a little bit and see if you can get a flag about yourself. Yep, thanks, Ryan. Ryan just copy pasted this slide, this link into chat. let me know if you managed to get a flag. And this binary is Linux, it's ELF in ELF format, so it's Linux executable. I saw a question from Zoom saying, asking, is the key supposed to be random characters or plain text key? It's supposed to be plain text key because this is just a toy example. So you will not be able to see like, random like a checksum key, but it will follow the format. If you see some format like CSE 365 with the curly bracket, then you're getting the key correct. Yes. Cool. Hold it for a while. I will ask you how to find it later. All right, I'll give everyone one more minute and then we will start. Okay. So, can I know how you solve it?
Yeah, I downloaded Getrust, I think you pronounce it. Getra.
Yes.
Yeah, and they have a really nice disassembler. So you can look for uses of character pointers.
Yes, uses of
But I-
character
it
pointers.
took me over to the main.
Nice.
In the main, it had the key, which is just pigeon.
Mm-hmm. Yes. Great. So, oh, but let me just check the key real quick. I forgot the key. Yes. The key is, 1 second. Yes, it is CSE 365 with the curly bracket, and then in the middle is good job. Cool. All right. Those that you haven't found the key, can you let me know, what you have tried? Can I have your name, by the way?
I'm Alex.
Alex. Okay, Alex tried the Ghidra. Alex downloaded Ghidra and then run it. For the rest of us, have you ever, what else are you trying? Yes.
I found the key using strings.
Good. So you use strings and you also find the key. That's nice. Any other, even though that this attempt fails, it's fine. I would just like to know what you have tried. It's okay that you didn't get anything from there. Have you ever tried to run it? Any of you tried to run this program? No? What did you try? Did you try to open it? Did you try to read the instruction of the program? Let me know if you tried to run it and managed to run it. Good. I saw people from Zoom try to run it. And raise your hand if you try to read it using, tools such as Option or any other kind of tools, try to disassemble, read the disassembly. Yes? Nice. We saw more people raising hands, trying to read it. Nice. Raise your hand or you're asking me a question? Yes.
So, okay, so when you went through that, I just decided to just great example that out here, are the flags different depending on the method you use?
Are the flags different depending on the tools that I use?
Yeah.
No, it shouldn't. For this particular one, of course, that if you write a fancy program, then the program can detect who is running this, what tool is running with it. But now I am just it's a constant, it's deterministic. So for whichever tools that you are using, you should always just get the same flag. All right, yeah, and then I saw someone from Zoom saying that I just opened it and the key is right there. Cool. Yes. Yes.
I actually just looked up it online.
Yes, you can open it and then you can just find it key. Awesome. Have anyone tried to Google, the answer? Or you said that you just Google the answer, right? Or you just
I looked at an online disassembly.
online disassembler tools. Awesome. Yeah. So let me start with I have also different kind of solutions. I'm not sure if I can go through all of them today, but let's start with some solutions and then we will continue if we do finish it today. All right, let me share my screen. 1 second. You should be able to see my terminal now. So and let me clean it up. Now we have nothing to know about, right? So first of all, I would check the format of the program. Now I notice that, okay, it is an F binary, it is executable. So I should be able to execute it. And usually the next I'm going to do is I'm trying to execute it. And of course you want to execute in a safer environment, although I won't set you a malware. So you don't need to worry too much about that. So this binary is trying to ask you, how many pages in this book, Harry Potter and the Philosopher's Stone. Actually, it's last year, there is a student that tried to answer, like, find the key by answering these questions directly. Just Google the question, Google this book, and then found exactly the number of pages, and then answered this correctly, and then he got the key. But yeah, here, we can also just crack this program, like reverse engineer the program, and then understand, if you just type a random number, of course, let me just page a little bit fewer, because there won't be that many pages. It will tell you that you're wrong and you need to keep going. And there are also students from last year that are trying to brute force this challenge, because he doesn't really know the answer, but he knows that pages, it must be something, probably from 0 to say 100, to 1,000. And he just like, try this brute force, write a script that can brute force interactive with this program using the way that we talked about last time, that you interacted with this program, you receive the line, you set the line, and then see whether or not you can get the flag in the end. Okay. Yeah, so this is like solution number 2, but those are challenge specific solutions. And let's just make it more general. Like whenever you come across a challenge like this, what you could do is, first you can try strings. This is a command that will just go through the data section of your program, and then output those strings that are readable from the data, like like reading aloud segment from your program. So we see that there are a bunch of values, numbers, some function names that we don't really care, some library names that we don't really care, and there's something like some strings, right? This is part of the strings that are the program uses while outputs those message. All right, and then just browse that, go through it, and actually here you see this sentence. It tells you that you're correct. This is your key. So in this case, you can find the key. This is solution number 1. You can use strings to get the key. But of course, in many cases, the key is not stored in the program. So in that case, you would not be able to read the string directly. Maybe the result is stored in a secret file. It's called maybe /flag that you have to have the permission in order to read and get the flag, right? And then in this case, strings will no longer work. But it's always to have this first attempt just to check, if there is a keys over there. All right. So this is first solution. And then the next, we are going to use Ghidra or IDA, like open your tool and then use this tool to static analyze it. I am going to use IDA. So this is how IDA looks like when you open it. And then you can find the binary, open it up. It will first popping up the window and tells you that this is the format that identified by statically reading the header file. And then it will show you the main function. Just like the entry point of this program, the main function. And you can read this. Let me just turn on the address. Usually I like to have the address show right on the left-hand side. Okay. So you see that this is the main function and try to execute something. I don't really care the instruction at this point. All I care first is, okay, like those comments, like those are some human readable natural language, right? So the first thing coming to my eyes are those natural languages. And I see those sentences saying, okay, you're correct or you're wrong, and it has you're correct and this is your key. Okay, and then you see that it has this specific place, and I will start to read those instructions from here because those are the interesting instructions. For me, I mean, not only just for me, I mean, for everyone, when you read the assembly, you don't really have to read it line by line. If you're doing that, it will take a lot of time. It's like when you read a novel book, you don't really read that letters by letters or word by word. You just like skim very quick. That's the natural way that you read a novel, right? And similarly here, when you read a disassembly, you don't really have to read it line by line. You can find the spot that you are interested in and then focus on those spots. So here I found that this is the spot that I'm interested in. And thanks to IDA, it gives you this so-called control flow graph. Like, it gives you, starting from, the end of the end of the basic block, it branch, it will jump into different positions. It will give you this graph showing how those possible execution will flows along with those instructions. And this is why it's called control flow graph. So I found this block, which is called basic block usually. So this basic block is something that I'm interested in. And I found this particular instruction, LEA, means load effective address. So what it's trying to do is it copies the address of this place to the specific register and then outputs, which is to output the value of the string. So I know that this must be the place that stores my keywords or something, message that I'm interested in. I just double click and I start the sentence, right? So you get your key. And these two methods that I just talked about, one is using string and other is used like IDA or Ghidra, are two static approaches that you can find the key. Next lecture, we're going to talk about dynamic solutions. All right, that's it for today. Thank you, everyone.